Okay, so I'm going to use two videos to go over section 11-11, which deals with applications of Taylor polynomials. And there are two applications of Taylor polynomials that we're going to look at in this lesson. Number one is approximating function values using Taylor polynomials, which that's really easy to do. All you're doing is plugging a numeric value into a Taylor polynomial and using it to estimate function values. We're really not going to do a whole lot with that because I think you guys can figure that out on your own. But we are going to spend quite a bit of time on number two, which deals with estimating error using Taylor polynomials. Okay, so to estimate error in using Taylor polynomials, we're going to take a look at what we have written down below, which is Taylor's inequality. You'll also see this like when you're asked to do problems involving this, it'll say like use a Lagrange error bound. Okay, so what these things do, Taylor's inequality and Lagrange error bounds, they calculate the maximum error of using the Taylor polynomial to estimate the value of a function. Okay, so again, like we use these Taylor polynomials to approximate the value of a function, and we can do that to a desired accuracy. Okay, so let's take a look at Taylor's inequality. Like the notation is really messy because there are a ton of different variables in here, but it's really not that difficult to use like once you get the hang of it. Okay, so what Taylor's inequality states is that if the absolute value of the n+1 derivative of the function f of x, so if the absolute value of the n+1 derivative is less than or equal to capital M for the absolute value of x minus a less than d, then the absolute value of r sub n of x, okay, so that's going to denote the remainder, so we'll talk about what that means in just a second, is going to be less than or equal to the m that we found up above, which you can think of the m as being like the maximum value of the n+1 derivative, divided by n+1 factorial times the absolute value of x minus a raised to the n+1 power. Okay, so we're going to use that inequality to estimate error. Okay, so what r sub n of x refers to, okay, so r sub n of x refers to the remainder or error between the actual function value and the estimate using the Taylor polynomial. Okay, so if you look, I have a couple of equations to the right. Okay, so this first equation here is saying like if we want to compute the value of some function f at some input, that is going to be equal to the Taylor polynomial t sub n of x plus the remainder, which is the difference between the actual function value and the approximation using the Taylor polynomial. Okay, so again, like the Taylor polynomial is not going to give us the exact function value, it's going to give us an approximation of the function value that is off by r sub n of x, which is the remainder, or the error or the difference between the function value and the Taylor polynomial. So if we take that equation that I started in purple and we solve for r sub n of x is going to be equal to the function value minus the approximation using the Taylor polynomial. Okay, so let's utilize Taylor's inequality and these Lagrange error bounds to do some examples. Okay, so this first one we're going to work together. So the directions here say that we can find the fourth degree Maclaurin polynomial for the function f of x, which is equal to the cosine of x, to be t sub 4 of x. So again, that's a notation that we use for a fourth degree Taylor polynomial. Again, a Maclaurin polynomial is just a Taylor polynomial centered at 0. Okay, so the fourth degree Taylor polynomial centered at 0 for f of x is equal to the cosine of x is going to be 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial. So we went over that in section 11-10. Okay, and then the question asks us to determine the maximum error when using the polynomial to estimate the cosine of 0.1. Okay, so what Taylor's inequality does is it calculates the maximum error in using a specific Taylor polynomial to estimate the value of a function. Okay, so let's go ahead and calculate that here. All right, so I'm going to be using this formula to do so. Okay, this one right here. All right, so if we want to calculate the maximum error in using the fourth degree Taylor polynomial, this is going to be the absolute value of r sub 4 of x. Okay, and that has to be less than or equal to m. Now, we said that m up above here, okay, what I'm boxing in blue, m has to be the maximum value of the n plus 1 derivative. Okay, so we're going to calculate that in just a second. Okay, we are going to divide that by n plus 1 factorial. So our n value here is going to be 4. So n plus 1 is going to be 5 factorial. And then we're going to multiply that by the absolute value of x minus our a value. So where this Taylor polynomial is centered is at 0, raised to the n plus 1 power. And if we're going to estimate the cosine of 0.1, we're going to wind up plugging 0.1 in the place of x. Okay, so we're going to replace x with 0.1 here. Okay, so the absolute value of r sub 4 of x, okay, so the maximum value or the maximum error of that fourth degree Taylor polynomial is going to be m. So we're going to calculate what m is in just a second, divided by 5 factorial, and then 0.1 minus 0 is just going to be 0.1. And sorry, I should have plugged in 4 in the place of n here. So when I do that, that's going to make the exponent for that factor 5. Okay, so what we want to do to calculate m is we want to go out to the n plus 1 derivative. Okay, so our function f of x is cosine, and we want to keep going until we get out to the fifth derivative. So f prime is negative sine, f double prime is going to be negative cosine, f triple prime is going to be sine, the fourth derivative is going to be cosine, and the fifth derivative is going to be negative sine. Okay, so what we want to do is we want to take the absolute value of the fifth derivative, negative sine of x. Now, if we think about the graph of sine and therefore the graph of negative sine, like the values of the sine function are bounded between -1 and 1. All right. So the maximum value for this fifth derivative here, the maximum value of that fifth derivative is going to be 1. That is the largest that function negative sign can be. Okay, so that maximum value is 1. We're going to plug 1 in the place of m. Okay, and this tells us that the absolute value of r sub 4 of x is going to be less than or equal to 0.1 raised to the 5th power over 5 factorial. And that is approximately 0. 2, 3, 4, 5, 6, 7 zeros. 8, 3 repeating, which is an amazing estimation for us using so few terms. Okay, so that Taylor polynomial centered at 0 for cosine, this one right here, that 4th degree Taylor polynomial, is a fantastic estimation for us. Like if I plug 0.1 into that Taylor polynomial, it is going to be a really accurate estimate of the cosine of 0.1. Okay, so again, Taylor's inequality, the Lagrange error bounds here, what they do is they tell us what the maximum error is when we use the Taylor polynomial to estimate the value of the function. Okay, let's take a look at the next example. It's similar to the previous example, but there's one part that's going to be a little bit different here. So the directions here say that the 3rd degree Taylor polynomial centered at x is equal to 0 for the function f of x, which is equal to e raised to the x power, is t sub 3 of x, which is 1 plus x squared over 2 factorial plus x cubed over 3 factorial. Again, you guys should remember that the Maclaurin series for e raised to the x power is the sum from 0 to infinity of x to the n power over n factorial. So that's where we get this formula from here. Okay, and the directions say to determine the max error using the polynomial to estimate e raised to the 0.5 power. Okay, so again, the absolute value of r sub 3 of x. Okay, so the maximum error for this is going to be less than or equal to m, which we'll calculate in just a second, divided by n plus 1 factorial. So that's going to be this number here plus 1. So that's going to be 4 factorial times x. So our x value is going to be 0.5 here, minus where our Taylor polynomial is centered, which is at 0, and then we're going to raise that to the 4th power. Okay, so the absolute value of r sub 3 of x is going to be less than or equal to m, so we're going to calculate m in just a second, over 4 factorial times 0.5 raised to the 4th power. Okay, so if we want to calculate what m is, again, this is our 3rd degree Taylor polynomial. We have to calculate the max value of the 4th derivative on our given interval, and our given interval is from 0 to 0.5. Okay, so our function value is e raised to the x power, the 1st derivative, 2nd derivative, 3rd derivative, and 4th derivative of that function are all going to be e raised to the x power. Now, if you think about e raised to the x power, like graphically, you have a function that is strictly increasing. So if we want to calculate the max value of the 4th derivative on the interval from 0 to 0.5, because that function is strictly increasing, we want to calculate the rightmost point on that interval. And the rightmost point on that interval is 0.5. So the max value of that fourth derivative is going to be e raised to the 0.5 power. Okay, so when we compute the value of all of the stuff here, that is going to wind up being approximately 0.00429. Okay, so the maximum error in using the Taylor polynomial to estimate the value of the function is going to be 0.00429. Okay, let's do this example together, and then I'm going to give you one to try on your own. All right, so this says that Taylor's inequality also gives us the condition on which the Taylor series expansion actually does represent the function. Okay, so if our Taylor series expansion does represent the function as n approaches infinity, r sub n of x approaches 0. Okay, so as n approaches infinity, the remainder goes to 0. All right, so what we want to do is we want to show that the cosine of x, which is equal to the sum from 0 to infinity of -1 raised to the n power times x raised to the 2n power over 2n factorial represents cosine for all x. Now, for us to mathematically show this, we must show that the limit as n goes to infinity of r sub n of x, so as n gets big, that remainder has to go to 0. Okay, so let's set up Taylor's inequality for this. So the absolute value of r sub n of x is going to be less than or equal to m over n plus 1 factorial times the absolute value of x raised to the n plus 1 power. Okay, so what we want to do here is we want to calculate the value of m. Now, when we take like the nth derivative of this function, like depending on what n is, the nth derivative of x can only be one of four things. Okay, so the nth derivative is either going to be plus or minus sine or plus or minus cosine, depending on the value of n. Because we know when we differentiate cosine, like the first derivative is negative sine, the second derivative is negative cosine, the third derivative is sine, the fourth derivative is cosine, and then that pattern is just going to keep repeating itself over and over again. Okay, so the nth derivative is either going to be plus or minus sine or plus or minus cosine. So when we take the absolute value of the nth derivative, or the n plus 1 derivative even for that matter, like the absolute value of that has to be less than or equal to 1. Okay, so the maximum value of the n plus 1 derivative, again, which is either going to be sine or cosine or negative sine or negative cosine, the maximum value for that is going to be 1. So we can replace m here with 1. So we get the absolute value of r sub n of x is less than or equal to 1 over n plus 1 factorial times the absolute value of x raised to the n plus 1 power. And when we take the limit as n goes to infinity of that, when we take the limit as n goes to infinity of the right-hand side, we're going to get some huge number in our denominator, which we're taking the factorial of, and that's going to make the limit on the right-hand side become 0. And since the limit as n goes to infinity of the remainder becomes 0, that means that that Maclaurin series represents cosine for all x. Okay, we'll pick up the rest of this lesson in the next video.